The QQ plot is a very important plot, especially to determine if a certain data follows a particular theoretical probability distribution. But before I get into the details of what a QQ plot is, first of all, you need to understand that the Q refers to the quantile. We are talking about a quantile plot. That's what we are referring to. Now, the quantile plot is what? Before I get into the details of what the quantile plot is really, I would rather go through what a quantile is and then get into this. Now, briefly speaking, I believe we already discussed that earlier, but let me just go through it as a recap as well. So you have, let's suppose I take some set of values which are equidistant to make things a little bit simpler for you to understand, but they may not be equidistant. Let's suppose you got some set of values like that. So you've got seven numbers, 1, 2, 3, 4, 5, 6, 7. And then from these seven numbers, there is something that you are used to, which is what we call the quartile. There is something that you are used to is the quartile. You have the lower quartile that you can find, you have the upper quartile that you can find, and there is another quartile that is called the median that you are used to. And we will first of all go through this quartile and show you what a quantile is. I'm going to go through the quartile and explain to you what the quantile is. This is a quartile because you have data divided into four parts. And then you have the quantile where the data is not necessarily divided into four parts. It can be divided into several number of possible parts if you want. So let's try to understand the concept of quartile number one as we are used to, and then get into that. So by the way, before we get into this concept of quantile, you have to understand that there are different methods that are used to compute quartiles or quantiles. All right. There are different methods that are used to compute these quartile or quantiles. And generally, if your data set is very small, like here you've got seven, these methods may vary a lot. All right, the result that you get from these different methods may vary quite a lot. However, when the data set is large, sometimes these methods do yield more or less the same solution. But for this course, we are going to adopt the method that I'm going to explain here, and this is what we are going to do in this course. We are going to adopt one of these methods I'm going to show you here. Now, what do we want? Let's suppose I'm going to find the median. The median is referred to as the second quartile, and we often write it as Q2. So if we want to find the median, the approach that we take here is to count. So to count the number of data points that we have, we've got 7 data points. We will add 1 to it. And because the median is the point that divides the data into two equal parts, so basically you can easily visualize it here. But if it is a data that divide the data, if it is a point that divides the data into two equal parts, so we can just take half of 7 plus 1. The median is half of the data will be below it, including itself, and half of the data will be above it, including itself. So then you have half of 8, which is equal to 4. So what do we want to do? We want to find out the fourth value, because here you've got what we call the median rank. So you look for the fourth value. You have the first, the second, the third, and of course you've got the fourth, which was already visually clear. So therefore, the median is 8. Here we go. So how to find the median? It's very straightforward. This is what we do. We can do the same thing now to find the lower quartile. Now, the lower quartile means what? 25% of the data would be found below it, including itself. All right, so roughly 25% of data would be found, not roughly, but 25% of the data would be found below it, including itself. So If we want to know what is the lower quartile, we just need to take 25%, which is 1/4 of 7 plus 1 as usual, which is 1/4 of 8, which is 2. So you have the lower quartile equal to the second value as you are seeing here. The second value is 2 and 4. So 4. So in other words, the lower quartile is 4. Here we go. The next step is to find the upper quartile. The upper quartile is the value for which 75% of the data is found below it or including itself as well. So what do we want to do then? We want to take 75%, which is 3/4, of 8, which is obviously 6 in our case. So, so what do we want to do then? We want to find out this sixth value, which is 1, 2, 3, 4, 5, and then 6. So the upper quartile in our case is 12 here. All right. So this is how we find these different quartiles. And what does these quartiles do? They roughly separate the data into equal parts, as you would see here. So you have the first quartile, you have a second quartile, you have a third quartile here. So roughly these data are separated into equal parts. Okay. Now, what do we want to do? These are the quartiles. The first quartile, the second quartile, the third quartile, which divide the data into 4 equal parts. One part here, two, second, and third here. The thing that we want to understand now is that sometimes we may wish not to divide the data into 4 equal parts, but we might wish to divide the data into far more parts than 4 equal parts. We want to divide the data into, let's suppose, 6, 7 parts, 8 parts, or whatever it is. If we want to do that, then we come to the concept of quantile. And of course, the idea is the same. We still want to divide the data roughly into equal parts. So what is quantile? If we look at the concept of quantiles, let's suppose I wish to compute something that we call the 50% quantile. The 50% quantile. The 50% quantile means 50% of data would be found below it, including itself. So if you think about it, the 50% quantile means the same thing like what we did here for the median. So the 50% quantile is 0.5 of 7 plus 1, which is 8. So it is equal to 4. So we need to look for the fourth value and we get the 50% quantile. If we want the 25% quantile, the 25% quantile means basically the first quartile. If we want the 25%, if you want the 25% quantile, the 25% quantile is the lower quartile. If we want the 75% quantile, then the 75% quantile is basically the upper quartile. But we have to understand that we don't need to stick ourselves to only these possible quantiles. We may wish to move on to other things. We might wish to look for more than 25. We might be interested in the 20% quantile. This is where we say that we are not going to divide the data into 2 equal parts, but we may wish to divide the data into several parts. And let's suppose I want to find the data for which 20% of the data will be found below it, including itself. What is the data point in there through which 20% of the data would be found below it, including itself? This is what we refer to as the 20% quantile. So I repeat, which I'm interested in determining the 20% quantile. The 20% quantile. If I want to find the 20% quantile, how do I get it? If I want the 20% quantile, the principle stays the same as I did earlier. But now you are going to do 0.2 multiplied by 7 plus 1, which is basically 0.2 times 8, all right, which is equal to 1.6, obviously. So if it is 1.6, you need to look for the value which is located at the 1.6 position. And what is the value that is located at 1.6? This is a 1, this is 2. So 1.6 is found somewhere here in the approximately in the middle of 2 and 4. It's going to be close to 3, but it's not necessarily 3. All right, it's going to be close to 3, but not 3 exactly. Given that it is greater than 0.5, it's obviously going to be greater than 3, slightly greater than 3. So let's try to determine what is this 1.6 value. The 1.6 value means that you have the first value, which is 2, plus you have 60% of, so you have 0.6% of the distance between 2 and 4 that you need to go through. So you have 1.6. Just imagine on a scale, you have 1, you have 2. 1.6 is where? You have 1.5 in the middle, and then 1.6 is somewhere here. So what is happening is that if you want 1.6, you basically need to move from the first position by 60% from the distance you have here to here. And the distance that we have from 2 to 4 is obviously 4 minus 2. So it is equal to 2 plus 0.6 times 2, which is equal to 2 plus 1.2, which is equal to 3.2. So we have found the 20% quantile. The 20% quantile is the value 3.2. All right. What does 3.2 means? 3.2 here basically roughly means that 20% of the data is found below 3.2, including 3.2 itself. This is what it would mean. So we may wish now to do like let's suppose I do something like 0.8. 0.8 like 0.8 means, like I said, 20, the 80% quantile. Let's suppose I want to find the 80% quantile. So the 80% quantile, if you've understood it properly, we just erase this part here. If we're talking about the 80% quantile, we are basically talking about 80% of the data is found below a certain number and below or equal to that certain number, including that certain number that we need to find. So 0.8 of 8, 7 plus 1, which is equal to 6.4. And what we need to do is to find the 6.4 value. So what is the 6.4 value? 1, 2, 3, 4, 5, and 6. So 6 is here, 12, and then you have 14 here. So what do we want to do is to find the 6.4. Obviously, we already found the 6 value. The 6 value is 12. Plus, you have 40% of the way from 40% of the way in the 20% quantile, we had 60% of the way from 2 to 4. But now you have 40% of the way, because 0.4 means you have 40% of the way from 6 to 7. So if 40% of the way from 6 to 7 means 40% from 12 to 14, which is equal to 0.4 into 14 minus 12. So you have 14 minus 12, which is equal to 12 plus 0.4 times 2. Basically, it is 12.8 that you have. So what we got here is we got the 12.8, which is the value that basically divide the data into such a way that 80% of the data is found below it, including itself as well. So this is how we find the different quantiles. We have a 20% quantile, the 80% quantiles, whatever quantile that you want to compute, you can easily compute it from a data set. Obviously, here things are equidistant, but if you add this value as 14 and this value, let's suppose it was 18 or 20, things like that, then let's suppose this was 14 and this was 20. This was 14 and this one was 20. Then the 20% quantile would be the same, it would not be affected, but the 80% quantile would not be 12.8, obviously. Let's suppose this was 14 and this was 20. So you would have to go from the same principle, 6.4, 1, 2, 3, 4, 5, 6 for an 80% quantile. 6.4 means 14 now, not 12, but 14 plus not 6.4 means 0.4 times 20 minus 14. So then, of course, things are not going to be 12.5. It's going to be obviously different. So, uh, excuse me, which is equal to 16.4 as you would see. All right. So you can compute it. So it is 2.4 plus 0.6 times 0.4 times 6, which is 2.4 times plus 14, which is 16.4. So here is what we have as quartile. By the way, we also refer to these quartiles as percentiles, to these quantiles, sorry, not these quartile, but these quantile as percentile. For example, when we are talking about the 80% quantile, we also refer to the 80th percentile, to the 80th percentile. If we are talking about the percentile, means you are referring to the same thing in terms of 100%, all right? In terms of 100%, but it's the same principle, same idea. So if you're talking about um, uh, 25% quantile, all right, if you're talking about the 25% quantile, it means that you are referring to the 25th percentile. In other words, the 25th percentile is the lower quartile. The median is the 50th percentile. The upper quartile is the 75th percentile. So this is how these different concepts are related, quantile and percentile. Now, why did I explain this to you? By the way, we can also, before I get into the quantile plot itself, let me just briefly show you this example. You had 2, 4 up to, let's take the original example as it was, and then for 12 and I got to 14 from what I recall. So what we do is that we want to compute these different quantiles using R. As I told you earlier, there are different possible ways of determining quantiles and so on. So what we want to do here is we want to use and try to find out the quantile in R using our method that we just shown here, right? So how do we get this? So for example, we've seen that the 20, uh, we saw that the 25th quantile was here, 25th quantile was here. We've seen that we've got, sorry, 25th quantile, excuse me, it's not this one. So the 25th quantile is here, yes, we go. So this is the 25th quantile. We got it here. We've got the median, which was 8 originally, from what we recall. We've got the 4 as the 25th quantile, that is the lower quartile. We've got the 50th quantile, which is a percentile, which is 8. And we've got the 75th quantile. The 75th uh, quantile is what? 75% quantile, sorry. The 75% quantile is 12. All right. 75% quantile is 12. So these are the different values that we got. And then we also got the 20% quantile, which is 3.2, and we also did for the 80% quantiles earlier, and the 80% quantile we've got 12.8 from what I recall. So what we will do is we are going to reproduce the same stuff in R. How are we going to do that in R? Let me just show you this quickly. So we add the numbers, let's call it X. So we add 2, 4, 6, 8, 10, 12, 14. And what we want to do is to compute the quantile. So one way of doing it is by typing the code quantile. The quantile gives you the different quantile that exists, all right, according to how you want to define these quantiles. For example, here we are talking about the quantiles of x, and I want to determine the quantiles of x like the one I just did. Let's suppose I want only the 0.25, that is the 20, 0.25, which means the 25% quantile, which is the lower quartile. I want the 0.5, which is the 50% quantile, and I want the 0.75, which is the upper quartile. If I want to do that, then I just need to select it as I've shown you here, C equal to 0.25, 0.5, 0.75, and I don't stop here. I need to add another argument to that function, which is type, because the quantiles offer R offers different possibilities, different ways of computing quantiles. And for us, we are going to be interested in the one that I explained to you, and this type is type 6. All right. Now, if you want to go and get into the details of what these are, you can do question mark of quantile, and then you will see what are the different types of quantiles that are computed. As I said to you, these different types will generally yield the same solution if you have a large data set. Like in our case, we've got a small data set. We don't expect to get the same solution through these different methods. These different methods can yield very different results from method to method. So, but for the sake of this course, we are going to take it as type 6, and we are going to enter, and you've got 4, 8, and 12 as we did earlier. So 4, 8, and 12, which are the 25th percentile, which is the 25% quantile, which is the lower quartile, which is the first quartile. And then we've got the 50% quantile, which is 8, the 50% quantile, which is also referred to as the 50th percentile, and the also referred to as the median and the second quartile. Then you have the 75th quantile, which is 12 as you saw here, and the 75th quantile is also referred to as the 75th percentile. It is also referred to as the third quartile and also referred to as the upper quartile. If we want to go a little bit more general, by taking 0.2, but not 0.2, by taking the 20% quantile, and we want the 80% quantile, then what we just need to do is to rerun that line of code, but now with 0.2 in there, which represents 20%. And then you also have the 0.8, which we wanted, and we do enter, and we'll see if we get the same value, which is 3.2, and this is what we computed, 3.2 earlier, and we will get 12.8 as 80%, and this is what we did earlier, it was 12.8. So you can still go and generalize all these into how many quantiles that you want. So here you've got 1, 2, 3, 4, 5 quantiles have been produced based on what you are looking for. So you have produced 5 quantiles. Now, these number of quantiles can be produced in terms of 100. You may wish to do a sequence of quantiles instead of 0.2, 0.25. You may do a sequence of quantiles starting from 0.1 to 1 in steps of 0.01. You can do it as many quantiles as you want to find out if from a data set. So this is a little bit what we understand by the concept of quantile. Based on that concept of quantile that I just talked about here, this is where now we can understand what a QQ plot is. It's very simple and very straightforward to understand what this means. So now we'll get into what a QQ plot means. But before I get into this concept again, let me just tell you something. When we say that there is 25%, we are looking for the 25% quantile, right? We are looking for the 25% quantile. One, we also refer to this as the 25th percentile. If you think about it properly, we can also relate that concept to probability by saying that there is a 25% probability that a value will lie below 4 or equal, will lie less than or equal to 4. That's what we mean. There's a 25% probability that a value will lie less than or equal to 4. Another way, if we talk about a 75% quantile, we are saying that there is a 75% probability that a value will lie less than or equal to 12. That's another way of doing it. And if we talk about the 50%, the 50% quantile. So what we are trying to say is that there is a 50% probability that there will be a value that lies less than or equal to 8, which means that 50% of the data is less than or equal to 8 and 50% of the data is above 8. In the case of 25%, which means that 25% of the data is found less than or equal to 4, and in the case of 75%, it means that 75% of data is less than or equal to 12. So we can relate that same concept to the concept of probability. So if you understood this well, now we can get into the concept of QQ plot. What is a QQ plot? The quantile plot is used to assess if the data comes from a certain theoretical distribution. That is the purpose of it. If we've got a set of data, let's suppose we've got this set of data that I just wrote, and you want to know whether it follows a normal distribution, whether it follows a Poisson distribution, all these kinds of things, you can go through a QQ plot to determine if the data comes from a certain particular theoretical distribution. All right. And now what generally will happen is that the QQ plot will take your data, your sample data or your data, and we'll find out the quantiles. Obviously, when we talk about quantiles, we are assuming that these data are ordered. Okay, like here you've got 2, 4, 6, 8, 12, and 10. Sorry, 2, 4, 6, 8, 10, 12, and 14. You don't have things like 2, 14, 8, 4, 8, 6, 10, and 12. You don't have something like that. We are assuming that these data have already been ordered like this. When the data has been ordered, this is where we find out the quantiles and so on. This is very important. The concept of finding median, lower quartile, upper quartile, the concept of finding quantiles, all right, the concept of finding percentile is based on the assumption that the data is ordered, obviously. So what we are saying here is that we have our data, we are going to order it first of all, and then we plot the quantiles that we obtain from the data against that of a theoretical distribution. All right, we basically need to do that. We take your sample data, sort it in ascending order, and then plot them versus quantiles calculated from a theoretical distribution. So basically, it's very simple. That's what we want to do. We want to compare the quantile from your data and the quantiles that you get from your theoretical probability distribution. If the points roughly align in roughly aligns in a straight line, then obviously it means that the quantile from your theoretical probability distribution is the same quantile as that of your data. And if they are the same quantile, then logically it means that the data as that follows that distribution that we are referring to, whichever distribution which we might be referring to. So basically, the principle is like that. You have the data points or the quantiles that you can get here, the quantiles from your data, and then here you have the quantiles from theoretical probability distribution. And this is what you do. If these quantiles are basically the same here, and they follow roughly a straight line, all right, they will not be exactly a straight line except if they come exactly from a certain distribution, but generally the data will have some variation around a line. But if they roughly follows a straight line, then logically it means that they are similar. However, if this is not the case, then it means if they depart substantially from a line, it means that the quantiles from the data is not the same as the quantiles from the theoretical probability distribution, whichever distribution it could be, normal, Poisson, whatever it is. So if they depart substantially, then it means that this data does not follow that particular distribution. That's how we get into the concept of knowing whichever a data is from a distribution or not. There is an example that we give you here. If you have a data, you have the sample quantiles that can be obtained. The sample quantiles means the quantiles that are obtained from your data, and then you have the theoretical quantiles which are plotted on the horizontal axis. So what you basically need to do is to compare the sample quantiles from the data that you had with that of theoretical quantiles. So you add the theoretical quantile from a normal QQ plot. Obviously, this seems to, not this seems, but this is a standard normal distribution. And then what happened is that you have here, you have the case of the different quantiles plotted. You just need to check the first quartile. Let's suppose you have a 20%. You are looking for the, let's suppose 10% quantile from the data. If you look for the 10% quantile from the data and you compare it with the 10% quantile from the normal distribution and you plot a point, then you are going to compare the 50% quantile from a data with the 50% quantile from a normal distribution and you plot a point, and you go on like that to compare these different quantiles with each other and see what you get. If you get something that goes around a straight line, then perfect, it is a normal distribution. Otherwise, it's not the case. Like in this particular context, wherever the data was before, we don't know the data, but when we plot the quantile from the data with that of a theoretical normal distribution, we observe that they roughly follows a straight line here. And if they roughly follows a straight line, we understand that this data comes from a normal distribution. That this data comes from a normal distribution. I give you some example here of what we call a normal QQ plot, all right? And there are different a possible behavior of a normal QQ plot. If you plot a normal QQ plot means the theoretical quantiles is from a normal distribution. And then you have the data, which is the sample quantile. You plot them. Let's suppose you got something that looks roughly like this. Okay, it's not exactly a straight line, but it's a little bit curvy. Then it is called a light tail distribution. That is, that distribution that we are referring to is not a normal. It departs from a normal by the fact that it is a light tail distribution. If a data looks like that and you're comparing it with a normal, so just remember here, when we are referring to theoretical quantile, we are referring to a normal distribution. And if the data lies like this, okay, it means that it is a distribution that is left skewed. In fact, the data is not a normal like this, but it is a distribution that is skewed to the left, something like this. If the data is like that, obviously it is a normal. If a data is something like this, it means that the data is bimodal. If a data is something like that, it means that data is heavy-tailed distribution. It's like a T distribution, maybe, something like that. And if data is like this, obviously it is right skewed because the above is left skewed. So you get an idea about the type of distribution by comparing it with a normal distribution. If you want to know what type of data you are dealing with, you can compare it with a normal QQ plot just to have an idea whether it is a light tail, left skewed, normal, bimodal, heavy tail, or right skewed. Or you may wish not to do a normal QQ plot, but you may wish to compare a data with another theoretical distribution. Let's suppose you have a Poisson distribution. You have a Poisson distribution and you have a data set here. You want to compare the quantiles from that data set with that of the quantiles from a Poisson distribution. And then you will see if the data again lies on a straight line, it means that the quantiles from the data and the quantiles of the Poisson are similar, which in other words means that the data comes from a Poisson distribution. So this is a little bit what we refer to as the quantile plot. So what we might be interested in doing now is to start drawing some of these QQ plot in R to see what it is basically. So we want to draw this QQ plot in R. So let's give it a try and see how we can plot this QQ plot in R. We will start by drawing the QQ plot from a rather a simple QQ plot that is available in R for the normal distribution. And we are going to have a look at the data set that is available in R. On Google Classroom rather, not in R, but on Google Classroom. And this is a data set that I've called it as insurance. I call the data insurance data set, and we want to see whether BMI really follows a normal distribution or not. That's what we want to know, if BMI follows a normal distribution. And we're going to have a look at that through the theoretical, through the QQ plot and see how it goes. Okay. Now, obviously, to be able to do that, you need to have a data saved somewhere. So what I'll do is generally I go through that procedure of setting my working directory. And when I've set my working directory, I'm going to read the data file. So I set my working directory as usual, and then I'm going to read the data file. I'm going to say data read.csv. It's already saved as a CSV file, which you need to do if it's not the case. So normally it's a CSV file. So and there was a header in it as you saw. So what we want to do is we want to plot a QQ plot for the BMI data. So to plot a QQ plot for the BMI data, there is a very straightforward way. So a QQ plot for the normal distribution, a normal QQ plot. That's what I want to draw. I want to draw a normal QQ plot to see if BMI follows a normal distribution. And how am I going to do that? In R, it's a very straightforward procedure. There is something that we call the QQ norm. The QQ norm enables you to identify whether a distribution is normally whether a data is normally distributed or not in a matter of only one line of code. For example, here, if I type QQ norm BMI, I would have an idea whether the data is normally distributed or not in a matter of seconds. All right. So, but if you want to have a look at what are the data that we have, we can do str data, for example. You will have different information like charges, like BMI, and so on. So let's try to see the whether BMI follows a normal distribution. So we just do QQ norm. It's a function that is available in R, and you don't need any package for that. You just type down QQ norm, and then you put BMI. As straightforward as that. And then you will see that data is as you are seeing here. So let me just resize that vertically. And here we go. You see that the data is not perfectly normal. It looks like a straight line, but there seems to be somehow some departure from the normal distribution, slight departure from the normal distribution. It is close to a normal distribution, but it is not exactly a normal distribution, especially because of what you see here in the curve from when you look at the cursor here. This is why I would not say that it is perfect. I would not say that it fits the normal perfectly, but it is close to a normal nevertheless. So if you really want to have a look at the histogram of a BMI to have a better idea of how it looks like, we can do that. And you will see that it looks close to a normal indeed. If you look at distribution, it takes really the shape of a normal distribution, but nevertheless, there seems to be some skewness in the data that what make it uh, a little bit skewed to the right side, kind of. But it is definitely not a normal distribution. It doesn't fit a normal distribution exactly, but it is close to it, as you would have seen here. Now, what we want to do is that this is the simplest way of drawing a QQ plot. Just by typing a function and you are done, especially for the normal distribution where you want to check for departure in the normal distribution. So let's just run this QQ norm and you will see here there is a theoretical quantiles which starts from around -3 to 3, which basically refers to the kind of standard normal distribution. But here the quantiles, you see that they are not on the same scale. If you're not on the same scale, this is why you can't just look at it 45-degree line, because the scale is different. Here, it depends on the data, on the scale of the data that you have. All right, you see clearly that the data is BMI, you have values like 30, etc., etc. This is why you have the quantiles, which are from around 20 to 50 and so on. This is important to understand that you can't just look at an absolute line of 45-degree to think about confirming whether it is a normal solution or not. Because here, the idea is to see if it looks like a normal distribution, even though it has been compared to the uh, theoretical quantile of starting from -3 to 3, it doesn't matter as long as it follows a straight line. But here, it is a slight departure from that straight line. So what do we want to do next? I want to show you another way of drawing a QQ plot. All right, I want to show you another way of drawing a QQ plot. So let me just show you that other way of drawing a QQ plot, using a without writing this function QQ norm. So the other way is, let's suppose I have a data now. Let's suppose I have a data and my data is indeed a set of normally distributed values of a set of normal random variates. All right, let's suppose I call it our norm. Our norm means you are generating no random variates from a normal distribution randomly. Let's suppose I generate 99 of those distribution with a mean of 30, and you have also the standard deviation of 10. Now, just bear in mind that when we talk about R does not, when we write down generally the normal distribution, we write it down in terms of its mean and the variance. But in R, you the parameter that is considered is the mean and the standard deviation. It is not the variance here, but 10 does not refer to the variance, but refers to the standard deviation of the normal distribution. So this is what we want. We have a data which is like that. So if you want to type the data, this is what we have. So here we are assuming that is we have got a data, just like we have BMI, we've got a data set like that. This is our data. So what do we want to do with that? We want to find out if this follows a normal solution. Obviously, one way of doing it is a very simple way, which is the QQ norm of data. QQ norm of data, which is a straightforward way of doing it. And here we go, you will see that it follows roughly that line, and it seems that it is normally distributed, obviously. Here, this particular case, it seems that it is normally distributed. And you will see also that the quantiles are again different because on different scales. Obviously, because data lie, the mean is 30. So you can't expect to have the same scale. But nevertheless, we know that the data looks like a normal distribution, which is indeed the case. Except for one point here, but it doesn't matter much. Overall, it is a normal distribution. So that's a very straightforward way of doing it. But we can do it in the other way by doing it from scratch. Basically, what we want to do is that if we have our data, which is here, obviously we know that it is going to follow a normal, but I'm just showing you the another way of doing it is that you can start creating quantiles. So the quantiles for the sample, you want to create the sample quantiles. The sample quantiles is going to be your y-axis, and the theoretical quantiles will be the one from your data, the one from your distribution. So the theoretical quantiles from that data is what I want to do first, and I'm going to call it y. If I call it y, I do quantiles as I explained to you earlier by using this function, and the quantiles of data. The quantiles of data from uh, the quantiles of data, but the quantiles of data, I need to ensure that I have the same number of data points here, right? It's the same number of data points, uh, or it may happen that I don't necessarily need the same number of data points. I could have written this as 100, I could have written this as 1000, it doesn't matter. But I just show you something here, is that if I do prop equal to sequence of 0.01, comma 0.99, and I do comma 0.01. What does this mean? It means that I'm plotting I'm computing the quantiles for that data starting from the from the 1% quantile up to the 99% quantile in steps of one. So the first one is the first percentile, if you want, or the 1% quantile. Then the second one would be the 0.02, which means the second percentile, or what we would say as the 2% quantile, and it will go on up to 0.99. And this is what I mean by steps of 0.01. So I'm creating quantiles from that data. Obviously, here what you do is you do enter, you have a data here, you are creating the quantiles from that data, which will be roughly the same thing as what it is here in order, if it is ordered. And then what you do next is I want to compare that. I want to compare that to, let's suppose, a normal distribution. But the fact that if I have a data of 30 to 10, I can compare it with a normal distribution with mean 10 and standard deviation 10, mean 30 and standard deviation 10. There is no point for me to do that. I can also compare it with a standard normal distribution, as simple as that, just like what it was here. I can just compare it with a standard normal distribution and I would have a rough idea whether it is the same or not. So let's have a look with the standard normal distribution and see whether it is comparable or not. So to compare with the standard normal distribution, what I will have to do is to create my x-axis. And my x-axis would basically be quantiles that I would obtain from a normal distribution. And the quantiles that I would obtain from a normal distribution can be obtained through uh, the function qnorm. You have rnorm, which generate random variates. Qnorms generate quantiles from a normal distribution. So I generate quantiles from a normal distribution, and I need to have the same number of quantiles that I have here. If you move from 0.01 to 0.0 to 0.99 in steps of 0.01, you will have 99 data points for the quantiles. So you will have 99 quantiles given. So if you have 99 quantiles, what I'll do, I'll use the function points 99. And when I'm doing that, I'm roughly basically saying that I want to generate quantiles starting from 0.01 to 99 if you want. It's basically the same kind of thing. Starting from the with not starting but rather generating quantiles, 99 quantiles. You are generating 99 quantiles from a standard normal distribution with mean 0 and variance 1. And this is what I want to do. I just missed the S here, I think. Yes, have a look. So here we go. We've got our X, we've got our Y. So X is what we have here, the quantiles from a theoretical distribution with a mean, from a theoretical normal distribution with a mean of 0 and variance and standard deviation 1. Uh, as I said to you, I could have done it with 30 and 10. Then you would see that the quantiles down there would be the same as the quantiles down up there. But it doesn't matter. I just want to compare that data, which has been generated from a 30 mean and a 10 standard deviation normal distribution, with that of a standard normal distribution as it is from the QQ norm function, right? So what I do then, I plot the x against the y. I plot the x against the y, and I just put the point character as 20 to make it a little bit neater. I'll do enter, and you will see that you will roughly get the same thing as you would have had here. Here we go. You get the same thing that you had earlier. All right. But the same thing that you had earlier is quite logical because you are plotting this same. You are doing the same thing like QQ norm here. What this function has done is basically what you have done here, all right, in those two steps. Now, you see that the interpretation is obviously the same. So you can change the y to sample quantile and x to theoretical quantiles. You can change the header x lab equal to sample quantile and then sample quantiles, and then you have y lab representing your sorry, x lab is your theoretical quantile rather, theoretical quantile, and your y lab equal to sample quantile. And then this is what you get. You get the same thing like a QQ norm function as you had earlier. So that's a little bit what another way of doing it manually. I repeat. So what basically you need to do is you need to have on your x-axis your theoretical quantiles, that is the quantile from a normal distribution with mean of 0 and 1 or whatever mean you want or standard deviation. And then you need to have the quantiles obtained from your data. And here the data is a series of random variates, normal random variates, a series of normal random variates from with a mean of 30 and a standard deviation of 10. So what we've got is we've got our data. We want to find the quantiles from the data. The idea is to have the same number of quantiles in the vertical as the horizontal axis. So the vertical is represented by your data, the y, the vertical, the y, and the x is your theoretical quantile. So that's a little bit how we can do it. So this is one way of doing it. The other thing that you can do now is also to check for a data that follows another distribution. There is no need for you, if you understand how to do it this way, you can also see whether a data follows any kind of distribution. It's not always, there is no need for always a main is equal to a normal QQ plot. You don't necessarily always need to go for a normal QQ plot. You can now check for a Poisson QQ plot. You can check if your data follows a Poisson. So let's do the same kind of thing. You've got a data, let's call it the sample, and you have our Poisson. Our Poisson means you generate random variates from a Poisson distribution. All right. Let's suppose I generate a certain number of variates from a Poisson. Let's suppose I generate 100 variates from a Poisson with a mean of 10. Right? This is what I've got. I've got a series of random random variates of Poisson distribution with mean 10. When I've got that, the next step, as I explained to you, is to obtain your quantiles from that data. This is our data. Let's suppose this is our data. So we want to obtain the quantiles from the data. So what we want to do is to generate quantiles. So to generate quantiles from the data, which is called sample, and I do the same kind of thing that I did earlier. I do probes equal to sequence of 0.01, comma 0.99, and 0.01. What does this mean? It will generate 99 quantiles. But of course, you may wish to change that according to what you want. But here you've got 99 points as you had earlier. So I want 99 points to be plotted. I could also change that into a different settings. I could plot from 0 to 1 in steps of 0.01. Whatever you want, you can do it. Okay. Now, this is our theoretical quantile. So if we type our theoretical quantile, the first quantile is 2. The 1% quantile is 2.99. That is the first percentile. So if you want the median is 9 in this data. In our data here, the median is 9, and it goes on like that. Now, our next step is to obtain, this is our data. We assume that this is the data. We've obtained the quantiles from the data. Our next step is to generate quantiles from a theoretical Poisson distribution. So we do X, and here, of course, instead of writing Q norm, we write Q plus because it is a quantile derived from a Poisson distribution. And you will need to do the same thing. You will need to create 99 data points. So you will create 99 quantiles, all right? That is what this X does, is that it will generate 99 quantiles from a Poisson distribution with these p points and with a mean of 10. Let's suppose we keep the same mean of 10. So we keep the same mean of 10 here and we do enter. For this one, it is better to have the same mean. For the normal distribution, it is comparable whenever you are comparing 30 and 10 with 0 and 1. It's okay. You still know whether it is following a normal. That's the idea. But in a Poisson, if you want to compare really the data, you need to have the mean. You need to know the mean. You can't use a different mean to compare. It won't make that much sense. So this is why I'm using the same mean, and you will see that you will have a straight line that will come from it. Let's have a look. So X is the theoretical quantiles, Y is our sample quantile, the data quantiles, X is our theoretical quantile from a Poisson with mean 10. So what we will do then is we plot the X and the Y. We plot the y against the x with a PCH of 18, let's suppose, or 20, whatever. Let's suppose 20. And then now we are not doing a normal QQ plot, but a Poisson QQ plot. I call it Poisson QQ plot. And then our X lab is theoretical quantile. Our Y lab equal to sample quantile. Sample quantile, so sample quantile. Quantiles. Here we go. I'll do enter, and you see that this data roughly follows a Poisson distribution because all the points seems to lie on a straight line, and the fact that the points lies on a straight line, it definitely follows a Poisson. And you see that here for this particular case, the sample quantile are on the same scale as the theoretical quantile, obviously, because we are taking the same data. It's quite normal because this is what we did. We generated data values from that distribution of mean from that Poisson distribution with mean 10. Logically, we expect to have this same behavior.